Okay, so we're going to go ahead and get started. Our guest tonight is Carl, K9LA, and he's going to be talking about a tour of the bands with the effects of cycle number 25. So whenever you're ready, Carl,
Okay.
if everyone else can mute if you're not muted, and we'll let Carl unmute there.
There we go. Well, I'm Carl, K9LA in Fort Wayne, Indiana. That's up in the northeast corner of the state. We're about 20 minutes from Ohio and 40 minutes from Michigan. We have 8 cats, so you're going to see probably some tails walk by here every once in a while. Hopefully they don't step on the keyboard, so that will help. Yeah, on the bands in 2025, I'll mostly be talking about 2025 on all the bands, but I'll make some comments on the following years too as necessary. So we'll talk about all 24 solar cycles first, and then cycle 25 status. We're going to have 1 peak or 2 peaks. Then we'll get into the bands, the general characteristics of the bands, and then 3 categories of bands: 160, 80, 75, and 60, 40, 30, 20, 17, and then 15, 12, 10, and 6. Hopefully it'll be obvious after I explain why it was broken up into those 3 categories. And there's some propagation references if you need some more information, because I certainly can't do everything in 40 minutes or whatever. Then just a quick summary too. Then I'll entertain any questions anybody has. Okay, here's an Excel plot of historical data. It plots the maximum smooth sunspot number for each of the previous 24 solar cycles. Cycle 1 began in 1755. You've probably heard of the Maunder minimum. That's when we had very few sunspots. That occurred from 1645 to 1715. So that was before our official data started. And why did it start in 1755? Because the solar scientists back then felt that they had pretty good data. So that's what happened. Now, if you look at the plot, what's kind of obvious is it's kind of cyclic in nature. We've gone through 3 periods of big solar cycles. For example, cycles 1, 2, 3, 4 were big. Cycles 8, 9, 10, 11 were big. Cycles, let's say 17 through 23 were big. Now that also says we've gone through 2 periods of small solar cycles. Cycles 5, 6, and 7 were quite small. Cycles 12, 13, and 14, and 15 and 16 were quite small. And of course, cycle 24 was small. So it appears that perhaps cycle 24 has ushered us into a 3rd period of small solar cycles. Well, how small was 24? Well, it's the smallest in our lifetimes, unless some of you got through cycle 14, but I doubt that. Cycle 19 there, the biggest in recorded history, peaked in 1957, I think it's March or so. And 21, that was a moderately big cycle, along with 22. And then cycle 23 came along, and it was an average cycle. In other words, if you take the all previous solar cycles, 1 through 24, and average them, cycle 23 was pretty much around the average. Cycle 6 was the smallest in recorded history. And I don't think it mattered that much back then because we didn't have radio yet, so whatever. So the big question is, will cycle 25 get us out of this apparent 3rd period of small solar cycles? So let's take a look at what cycle 25 is looking at. This is data through December 2024. We have 55 months of smooth sunspot number data since solar minimum in December 2019. Cycle 25 is that big, thick red line. And I have 4 other solar cycles on there. So it gives us an idea of how big cycle 25 is compared to some other solar cycles. At the bottom is the green, that's cycle 24, the smallest in our lifetimes. And the orange is cycle 23, which is pretty much an average cycle. Blue is cycle 21, that was a good one. Moderately big, and it peaked in December 79. And of course, I mentioned cycle 19. Okay, March of 1958, I was off by a year. And it was the largest cycle in recorded history. There may have been bigger ones. We just don't have any data, any good data. Well, what's the good news? The cycle 25 has surpassed the maximum of cycle 24, and it's headed towards the maximum of cycle 23. Will it get there? All we can do is just wait and see what happens. The month of January has been kind of decent for generating sunspots. So hopefully that means we'll maybe continue to rise a little bit. Let's see what else. Well, that's about it. All you can do is keep your fingers crossed if you're an aficionado of 15, 12, 10, and 6 meters. And we'll see why that's important. So I mentioned smooth sunspot numbers. What are smooth sunspot numbers? Well, here's a plot of cycle 23 in terms of the daily sunspot number. That's the red data. That's very spiky. So it's kind of hard to tell what a solar cycle is really doing. So what you can do is take a month's worth of data and average it, and that'll be the monthly average or the monthly mean data. That's in blue for cycle 23. It's still kind of spiky. So let's go one step further and do some more averaging. We'll take a 12-month running average of monthly means. And that's the green, and you can see why it's called a smooth sunspot number, because the curve is very smooth. You can do the same thing with 10.7 centimeter solar flux, and you'll see the same thing. The daily data is very spiky. The monthly mean data is better, but still spiky. And then the smooth 10.7 centimeter solar flux will be nice and smooth. So smooth sunspot numbers are used for 2 reasons. One is it's the best way to see what a cycle is doing. It's also the official measurement of a solar cycle. It eliminates all the spikes, and you can see very clearly that there were 2 peaks to cycle 23. There was the first peak, there was an obvious valley in between, and then there was a second peak. So that's one reason why we use smooth sunspot numbers. Also, at the moment, it's the best correlation we have between what the ionosphere is doing and what the sun's doing. That's through the smooth sunspot number. We don't have daily predictions yet because we just don't understand well enough the short-term variation in the ionosphere. And I would hope that Eric Nichols, KL7AJ, talks about that tomorrow night. I'm not talking too much about how the ionosphere works, so that's good that he's doing it. Cycle 24, it had 2 peaks. We'll see that in a little bit. And cycle 25, like I said, we'll have to wait and see. So here is the data from 24 and 25. The green dots are the total sunspots in both solar hemispheres. The blue curve is sunspots that emerged in the northern solar hemisphere. Orange are the sunspots that emerged in the southern solar hemisphere. Now, cycle 24, you can see why it had 2 peaks, the green dotted curve. The northern hemisphere was active initially. The southern solar hemisphere wasn't. Then they switched places. Orange southern hemisphere was very active, whereas the blue northern hemisphere was quieted down quite a bit. Now, there's the data so far on cycle 25. It looks like maybe the northern hemisphere has peaked. All we can do is wait and see what happens. The southern solar hemisphere is still going up. So we'll just have to wait and see. So does that mean there have been two peaks? And I just don't think you can say that yet, because that first peak, because of the northern hemisphere, it's kind of a peak, but there's no really obvious valley in between. So we'll have to wait and see what happens. But if I had to bet, I'd bet that we're not going to have two peaks, but that's okay as long as the total sunspots keep going up. That'll get us better propagation on the higher bands, higher HF bands in 6 meters. So what does it take to make a QSO? Well, there's two things. Most of our QSOs are made via the F2 region. The F2 region is the one with the most ionization, most free electrons, and also it's the highest up, which gives us the longest hops. So to make a QSO, there's got to be enough F2 region ionization to refract or bend the signal back to Earth. You can see its solar minimum there on the left at 28.4 megahertz, 10 meters. It's going to go right through the ionosphere. There's just not enough F2 region ionization to refract it back to Earth. But for its solar maximum on 10 meters, you can see what happens. The ionosphere does bend it back to Earth. And what does ionization mean? Well, that's just the number of free electrons that were produced by being detached from atoms or molecules by the extreme ultraviolet radiation from the sun. I should comment that 10.7 centimeters solar flux has nothing to do with the ionization process. It's just a proxy for the extreme ultraviolet radiation, just as sunspots are just a proxy for the extreme ultraviolet radiation. Now, in addition to the signal has to get back to Earth so we can hear it, there has to be low enough loss to be able to hear the signal with your ears or to decode the signal with a digital mode. There's quite a number of parameters that determines the total loss. We can control some of them, and there's other ones we just can't control. For example, we can control transmit power, increase your power up to 1.5 kilowatts. That'll help. Make a better transmit antenna by increasing the gain and the pattern, so you can point it at the target location. Receiver sensitivity. Most HF receivers nowadays are pretty similar in sensitivity, so that's not too much of an issue. And of course, the receive antenna gain and pattern you can increase if you need to, if you have a separate antenna. That kind of mostly applies down to the low bands. Now, we can't control free space path loss, which is just the spreading of the wave as it progresses. We can't control ionospheric absorption in the D region. We can't control ground reflection loss. If it's a multi-hop path, that's what's going to happen. There's going to be several ground reflections. We have no control over that. And there is polarization loss, which isn't a biggie. Of course, if your line of sight with a horizontal antenna and a vertical on the other end, that's going to be pretty high polarization loss. But ionospherically speaking, it's probably several dB or so when your antennas don't match what the ionosphere dictates that what dictates what the polarization is. So that's a subject that is very interesting and somewhat complicated too with the math. General characteristics of the bands. Here's where I talk about the three categories that I outlined earlier. There are those bands that are critically dependent on loss. And of course, they're best around solar minimum when the D region absorption is minimum. Those bands are 160, 80, 75, and 60 meters. And why are they critically dependent on loss? Well, that's because ionospheric absorption in the D region is inversely proportional to the square of the frequency. So the lower the frequency, the higher the loss. It's also why when you get up to 10 meters, The loss is not very much in terms of absorption. And that's one of the contributors to making 10-meter signals well above the noise. Whereas 160 and 80, you may have to fight with signals down near the noise. There are those bands that are critically dependent on ionization. They're best around solar max, where we are right now. Those are 15, 12, 10, and 6. Why are they critically dependent on ionization? That's because the amount of refraction is inversely proportional to the square of the frequency. So the higher in frequency, the more refraction you need from the ionosphere. So that means you need lots of sunspots, which corresponds to lots of extreme ultraviolet radiation, which gives us lots of free electrons that can refract those signals back to Earth. Now, all those 4 bands that are in between, 40, 30, 20, 17, they're somewhat dependent on loss, and they're somewhat dependent on ionization. What that tells us is that generally they're best throughout a solar cycle. And one of the first kind of truths that I heard when I was a novice was that if you can only put up one antenna, put it up for 20 meters, it'll be good throughout a solar cycle. You could also call these bands the transition bands because they're transitioning from being dependent on loss to being dependent on refraction. So that's why they're kind of broken up into 3 categories. So let's talk about 160, 80, 75, and 60. During 2025, they're going to be good for local QSOs during the day and night. Of course, the daytime QSOs will be shorter than the nighttime QSOs, but they're still there. And that's why most traffic nets are on 80 meters and 75 meters, because 80 meters and 75 are really good for NVIS, near vertical incident skywave propagation. Now, long distance nighttime QSOs are possible. Remember, we're at solar max, so it won't be as good as that solar min. You just got to keep your butt in the chair and listen really hard, because those signals will be probably down around the noise level, or maybe on exceptionally good nights well above. Of course, you should also always pay attention to sunrise and sunset times on these bands if you're looking for the longer distance contacts. In other words, DX contacts. Slide 9, the next slide, is going to talk about gray line and also about sunrise sunset enhancements. One of the problems with the low bands, of course, is man-made noise and QRN, which is lightning discharges from thunderstorms that propagate. Those lightning discharges can propagate all around the world. So the best way to mitigate man-made noise is go track it down and fix it. As we go forward into the electronic age, our homes probably have lots of switching power supplies. So be advised that you better take a look at that if you want to concentrate on the lower bands. They're also called wall warts. So you may have a lot of work to do just inside your house, and then you can work on the neighbor's stuff in power line noise, right? Oh, that's good stuff. Another way, after you fix your noise, man-made noise, or at least get it down as low as you can use antennas with directivity, and we'll talk about them on slide 10. I just caught an error here. It says see slide 9. It should be see slide 10. And also see slide 10 probably should be see slide 11. So I'll correct that when I send the PDF to Anthony there. So here's an example of a gray line propagation and also sunrise sunset enhancement. I consider them to be 2 different things, although it can get confusing at times. On the left is a gray line propagation. That's when the path between the 2 stations falls on the terminator. And that's what I'm showing there. I just picked a St. Louis, kind of mid-America to VQ9. You can see the short path in red follows the pretty much follows the terminator, or lies on the terminator, or is very near. And the long path, which goes to the southwest out of St. Louis, follows the terminator also. Now, one thing I'll comment that the only gray line enhancements that I've ever seen and read about are on the long path. So, you know, that's how you make long distance contacts on 160 and 80, generally via via gray line enhancements. Now, on the right is a sunrise enhancement. And that's when the short path is approximately perpendicular to the terminator on the east end of the path. There's an example short path from St. Louis to Italy. A lot of people during the contest stay up until they catch European sunrise, and there can be a nice enhancement for a bit. You know, tens of minutes, I've seen that. And there's also sunset enhancement. For example, if St. Louis looked at, for Italy at St. Louis sunset, you might also catch an enhancement, but typically it appears that when the terminator's on the east end, that's better than when the terminator's on the west end of the path. So we'll see what, just listen and maybe you'll see some examples of both. So mitigating noise. Well, here's what man-made noise looks like in a 500 hertz bandwidth. That's from the ITU document, radio noise. What it shows is the man-made noise in that CW bandwidth versus frequency. On the left vertical axis is noise in dBm. And I translated that on the right vertical axis to S units, assuming S9 is minus 73 and an S unit is 5 dB. That makes it a little bit easier. So then using 6 dB per, but whatever, close enough. Now that data is from the early 70s. So you got to watch it because it's worse now, especially on the lower bands. There was a good study several years ago by ham operators in the Netherlands. That's their national organization, is VERON, Veron, I guess is what they say. I'm sure that's some words in Dutch. It's worse now, like I said. And what their data showed is the noise in a residential environment is about 10 dB worse now at 1 megahertz. It's about 5 dB worse at 10 megahertz and about 2 dB worse at 30 megahertz. If you look at a rural environment, it's affected less, but there's still an effect. Now, I talked about using antennas with directivity. On the right there's an azimuth plot of the pattern of a vertical or a low dipole. It's pretty much omnidirectional. Therefore, it receives noise from all around the compass. Now, what you can do is put up a receive antenna with directivity. Foursquare, Beverage, a bog, a 9 circle array, a bunch of other ones out there too. What it does, you can see there's its azimuth pattern. It's a decent one. It can be a lot better. It receives less noise from all around the compass and then improves your signal to noise ratio so you can hear signals better. Of course, the ultimate goal is to have a receive antenna on the low bands that looks like a Yagi on 10 meters, you know, very narrow forward lobe. But of course, that takes a lot of real estate, which most people don't have. But you can make an improvement with I've had a bog, beverage on the ground. I've had beverages. I had a shared apex loop, and they all worked great and helped a lot. But if I had more land, I could have done a lot better. Okay, now let's get to those 4 bands where ionization is critical. course, they're going to be great in 2025 in the coming fall and winter months for long distance QSOs during the day, and in the fall and, like I said, in the fall and winter months. The least critical is 15 and the most critical is 6 meters in terms of ionization. And just remember that the amount of refraction is inversely proportional to the square of the frequency. So the higher in frequency you go, the more refraction needs to get done to get it back to Earth. Now, the F2 region, thankfully, doesn't totally go away after sunset. And recombination of a free electron to the positive ion is a slow process. That's why 15-12-10 can be opened several hours after sunset. And that's going to depend on the magnitude of the solar cycle. I'm sure we saw some, at least I saw some on 10 meters here. It was a couple hours after sunset and I could still hear Japan stations. And again, it depends on the magnitude of the solar cycle. It would extend longer into sunset if we had a bigger cycle. Now, the maximum usable frequencies will be reduced during the summer months. That's because the atmosphere undergoes undergoes a change in the summer months, and it results in less free electrons being formed. Now, it says slide 12, that should be slide 13, so I'll correct that one. But one of the good things that's coming up is 20 meters is going to be open all night this summer. Well, mostly it's spring and summer. We'll see that on slide 13. Man-made noise is less, the higher you go in frequency. You saw that in the previous slide. And 6 meters, well, we'll talk about F2 propagation, sporadic E propagation, and tropospheric ducting on slides. Probably, probably 14 through 18, I'll bet. I'll get all that corrected. So here's 15, 12, and 10 in the summer months. What you're looking at is the maximum usable frequency from K9LA to England at 1500 UTC, that's during the day. The results are from VOACAP, and it shows the MUF for each month of the year at 3 different levels of a solar cycle. One thing that's very obvious is during the summer months, the MUFs are lower. And that happens every year. You can't do anything about it. Of course, what it hurts is the IARU contest in July. The only really long distance contacts on 10 meters will likely be via sporadic E if sporadic E happens. Now, I also mentioned that 20 meters should be open all night in the spring and summer months. And here's some data that shows, like if we have a small solar cycle, that says 20 meters won't be open at all throughout the night. But where we are right now at a smooth sunspot of 150, we should see 20 meters in April, May, June, July open worldwide during the night. So that'll be good, of course, for field day too. If the solar cycle gets bigger, it's just going to have 20 meters open during more months of the year during the night. But I don't think we're going to get too much above 150. So kind of look, maybe start looking in March and maybe even into August if things go good. Okay, 6 meter F2 propagation. Now, for the MUF to reach 50 megahertz, on many days of the month, we need a very big solar cycle, like cycle 19, 21, and 22 also. We'll go back and look at slide 3 at the all 24 solar cycles. You'll see that 21 and 22 are up there too. Now, cycle 25 right now is big enough to offer opportunities during the daytime on some of the days in the fall and winter months. But generally, 6 meters needs an enhancement to get the MUF to 50 megahertz. And here are 3 examples of enhancements. One is if your path stays at a low latitude, that puts it in or very near the robust equatorial ionosphere, which is has the most ionization in the world around the equatorial ionosphere. So a path from southern US to VK and ZL that says that that's a good shot for 6 meters. Now, if there's a medium or a moderate short-term spike in the K index, that could improve the MUF. So here's an example. Here's the MUF of over the Boulder ionosonde, assuming it's the midpoint of a 3,000 kilometer path. You can see on October 1, 2, 3, 4, 5, and 6, the MUF was around 20 megahertz. October 2018, that's one of the California QSO parties. And on Saturday, I did not hear any W6s on 10 meters. But what happened on Sunday? Well, you can see on Sunday, the K index spiked up to 5 for three of the 3-hour periods. And look what happened to the MUF on Sunday. It went up to just above 31 megahertz. So there were lots of W6s to work on Sunday in the Cal QSO party. So just keep an eye on a moderate spike in the K index, and take a look at the higher bands, 50 megahertz, even 10 meters too, and 28 megahertz. Now, there can always be an area of unusually high ionization in the right place. And that's because the ionosphere is not really homogeneous. It's got little dips and peaks in it. And we can't predict that at the moment. I don't know if we ever will, but there's sure a lot of research going on. So we might be able to catch some of those short-term openings, but right now, you just got to sit in a chair and have the radio on. You might catch one. Okay, sporadic E. Here's a plot of some old data, which is still relevant, of the percentage at a given time in a month that sporadic E could occur. I've shaded in the highest probability areas, and you can see in the summer months, around late morning and early evening local times is when you should be on. In the winter month, mostly December, but we've seen it in November and even January. Early evening local time is a good time to look for sporadic E. Now, we certainly didn't have much sporadic E last summer. Hopefully we'll be better this summer, and I'm not sure there's a way to predict it yet. So we just got to have the 6-meter radio turned on and listening, or look at various internet websites that give us an idea what's going on. And 6-meter tropospheric ducting, we'll probably have some good stuff in the summer. There's a curve. There's a plot there. That curve on the left is a normal temperature variation in the troposphere. It starts at something like 20 degrees centigrade, and it just continues to decrease as it goes up higher in altitude. Now, tropospheric ducting requires a temperature inversion. That's what that curve on the right shows. You can see the temperature goes up till about 1,000 meters. Then the temperature decreases up until about 1,000 meters. Then the temperature increases for a bit, and then it starts decreasing again. And what's important is the depth of that inversion. Temperature is primary, but humidity is also involved. So that data comes from radiosondes, which I think a lot of stations release 2 balloons every day, and they take data, and you can see what's going on in the troposphere, and that may relate to some ducting on 6 meters. Now, here's a plot of how much of an inversion depth is required. The data from 70 centimeters up to 24 gigahertz came from the ARRL's UHF microwave experimenters manual. And I extrapolated that curve, hopefully it's correct, down to 2 meters and 6 meters. And it says that the tropospheric ducting on 6 meters depends on an inversion depth of about 450 meters. And that is tied to the change in the refractive index of the atmosphere to 0.25 per meter. If there's a stronger change, then the depth doesn't have to be as deep. But all you can do is look at plots and maybe take a guess. Hey, I might want to get on. Of course, you also need stations in the right place, which is another thing. K7CW reported a possible tropo opening on 6 in Washington State back in the early 70s during the ARRL June VHF contest. And there were lots of QSOs between KL7 and southern W6s. So 6-meter tropo appears to happen, but it's certainly not as prevalent as like 2 meters or 70 centimeters. And of course, if you want to get an idea if there might be some tropo, there's the Hepburn Tropo Index. There's the URL above the map. You can select a region of the world, and what you'll see is a heck of a lot better, more opportunity during the summer months. This was on January 16th, and it doesn't look too good. But the summer months will be better. So just be aware of that as we start getting warmer. Now, just a note that if you want to know what the bands are doing right now, well, there's several ways to do it. One very easy way is dxmaps.com. You can select a view of the world. This is a worldwide view, and the band, this is 10 meters. This happened on January 16th, which wasn't about a week ago. And it was from 1807 to 1815 UTC. You can see all those QSOs. Looks like a sporadic E was going on. In the States, looks like there's might be some trans-equatorial propagation down to deep southern South America. There was some propagation, probably F2 region into Europe and South Africa. Other methods, WhisperNet, PSK Reporter. You can listen to the IARU NCBXF beacons. You can transmit and listen to your signal at remote receivers in the reverse beacon network, and you can tell what propagation is pretty much real time. Since we don't have daily predictions, this is a great way to understand what's going on right now. Okay, how about disturbances to propagation? Well, there are 3 of them. Geomagnetic storm. It's caused by a coronal mass ejection or a coronal hole. Causes elevated K indices, and it can deplete the F2 region of electrons. In other words, lower MUFs, lower maximum usable frequencies for several days or longer. Solar radiation storm. It's believed to be caused by a CME in conjunction with a big solar flare. What happens is protons in the solar atmosphere are accelerated to relativistic speeds, velocities, and they funnel into the polar cap, and that results in more D region absorption in the polar cap for a couple days. So if there's more absorption in the polar cap, that means that could affect an over the pole path. Of course, the West Coast has more to worry about because many of their European paths go through the polar cap. Radio blackout, that's caused by a big solar flare. It causes more absorption in the D region due to radiation at X-ray wavelengths on the daylight side of Earth. And this results in signals on the lower frequencies disappearing for an hour or so. So in terms of which one's most severe, I believe the geomagnetic storm is, because it can really screw up the F2 region for several days. Now, here's a picture of a solar cycle. Yeah, I'm sure everybody knows that the average length of a solar cycle is about 11 years. Some are shorter, some are longer. Average is 11 years or something like that. Average rise time is 4 years. The average decline is about 7 years. Solar flares and CMEs are most prevalent at solar maximum where we are now. Coronal holes are most prevalent on the declining side of a solar cycle. So since we're at solar maximum, we have to take the bad, which is solar flares and CMEs, with the good, high MUFs. Now, I'll just make a comment that coronal holes generally are worse than CMEs. And we'll start seeing that when cycle 25 starts going down, probably around 2027 or something like that. So here's a bunch of propagation references. ARRL handbook and the ARRL antenna book. Both of those chapters were combined and put into a here to there radio wave propagation from the ARRL. Bob Brown, some of you West Coasters may be familiar with Bob. He's a silent key, unfortunately, but he wrote the Little Pistol's Guide to HF Propagation. It's out of print, but it's on my webpage. So you can just go to K9LA.us and you'll find it there. Shortwave Propagation Handbook was updated in 2021 from its 1995 version. 1995 was quite a bit ago. Unfortunately, it's out of print and doesn't help that CQ's not around any longer either. Not sure where you can get that. Don't know what else to say. G0KYA. Steve wrote a Radio Propagation Explained. That's a RSGB book, and you can go online and buy it from him. Or you can just look at my website. I got a lot of propagation stuff on there. So here's the summary. Cycle 25 has surpassed cycle 24. This is great news for 15, 12, 10, and 6 meters. We'll probably see cycle 25 extend out to at least 2027 before it starts its decline. So we still got a couple of years of 15, 12, 10, and 6 meter propagation. Should be pretty good. But don't give up on the low bands. You can still make QSOs if you're dedicated. Use the internet to see what's going on right now on the bands. And just get on the air and have some fun. Use FT8 for its advantage over sideband at CW, especially on 6 meters. And I encourage you, if you can hear FT8 tones with your ears, get on CW and sideband. CW should be doing good too. And even sideband if those FT8 tones are strong enough. So like to get some of those legacy modes back on 6 meters. Makes it more fun for everybody. So that's all I had, Anthony. If anybody's got any questions, I can certainly try and answer them.
Well, thank you very much, Carl. What we'll do first is we'll go through the stuff in chat. Barry, do you have anything in chat? I don't think we have anything in chat. So what we'll do is if you have a question, go ahead and raise your hand and call on you and unmute then.
Yeah, we're good in chat.
Okay. Any questions from anyone?
Carl did just a fantastic job explaining everything. He probably answered everybody's questions.
Thank you. Hopefully, yeah, it's tough to do something in 40 minutes.
Yep.
And all the cats, I think, went to bed too. I haven't seen one.
Well, this last week I was doing a general class. I was teaching a general class, and I had about 15 minutes to go through everything that you went through today.
Oh, wow.
In a much smaller manner, but it was a great to hear everything again. And I came up with a little thing using AI. I was playing around with it, and I'll show that in a few minutes here. But any other questions from anyone?
And remember, this stuff is the subject of many university courses that are months long. So it's good to have a concise summary.
Okay. Yeah, like I said, Anthony, I'll send you the PDF with the right slides referenced. I must have added a slide up front, and that screwed up all the slide numbers on the other slides. So, oh well.
I know what you mean because I've stopped doing that because whenever I do that, it
Yeah.
means that I will get the wrong number or we'll change something.
Yep.
So this is the little slide. This is the I put in the chat the little slide that I created for the students about the evils of the D layer. Nothing ever
Oh,
good comes
okay.
from the D layer, and the E skip, F skip, and moly the hoarder of ground losses. So
There
these
you
are
go.
the four propagation characters that I came up with for my class today. I like creating AI images lately. So,
Okay.
And remember, when you're listening on the bands, just because you don't hear anything, transmit. You will be surprised what you can get.
Yep. Good point.
any other questions? It's a
Gene has
quiet
his,
group tonight.
Gene has his hand up.
Oh, go ahead, Gene.
Good evening, everybody. Great presentation tonight. This is Gene, N3XUS from Killeen, Texas.
Okay.
My question is concerning general meteorologists' weather predictions. How much do they take into effect or take into account solar weather in their daily predictions for either that day or the days to come?
Well, I may not be the right guy to answer it, but I'm not sure they use solar stuff too much to predict terrestrial weather. I think they should, but I'm not sure it's very possible. Maybe someone else can answer that better than me. No. You know, there's a uh, Jim Bacon, G3YLA. He's doing a lot of interesting work on 6-meter sporadic E. And what he looks at is terrestrial events that could help trigger sporadic E. And hopefully his research may someday make our predictions for 6-meter sporadic E a little bit better. Because there are things that happen in the lower atmosphere. You know, you got the jet stream and all that stuff, and there's turbulence, and it's interesting to listen to him talk about that. So,
Okay, thank you very much.
okay.
Another very interesting person is CT1BOH. He's done a lot of stuff with these little, I think he refers to them as micro MUF points between different locations that pop up, and he's got a lot of very interesting things too.
Yep.
Other questions? Well, you got them all filled in, it sounds like tonight, Carl, and they all just need to get on the air now and practice some of those things you talked about.
Yeah.
So in the meantime, I've been sitting here making FTA contacts on 160 because it's great nighttime. It's a great evening tonight. Very low absorption, and things are working really well. So get on the
Good.
air, use some of Carl's band suggestions, and prove them. That's the best way to. That's the most fun about propagation when it actually works. When you try it and it works, and you get results.
Yep. Okay.
Well, thank you very much, Carl.
You're welcome.
Just a reminder, again, we'll be here Thursday night for RATPAC. Tomorrow night will be Eric, KL7AJ, and he'll be doing a propagation-oriented talk also. And every Wednesday and Thursday. 73, everyone.
Are you going to
Thank you.
send out? Are you going to send out or just use this?
Yeah, when you send me the link, I will the recording of this will be available probably Friday or Saturday, and when you send me the slideshow, I'll attach that to the recording.
No, I mean the Zoom invite. I can just use tonight's for tomorrow night.
Yes.
Okay.
Yes.
Okay. Good.
Same Zoom room every night. So if
Okay.
you never
Great.
forget it, you can always go to ratpac.us/Zoom and get the link from there. Or if it
Okay.
happens to change in between a week, we'll always have the newest one there, hopefully.
Okay. Good enough.
Okay. 73, everyone.
73.
Can I go ahead and close the meeting? It's going to close it for everyone.
Good night, all.
See you, Carl.
Bye-bye.
to see you again. Thanks for the presentation.